Good afternoon. Let's start our visual slope online training session 5. Again, thank you for attending. The topic today topics are pi-supported reinforced embankment and the seepage analysis. Um, let's just go to a little bit detail for that. We'll discuss about the pi-support embankment, the design mechanism, and the design example. Actually, this topic is not only suitable for power-supported embankment, but it can also be used for composite foundation. Uh, for instance, if we have a grocery store or warehouse, the large area, but uh, the foundation soil is very soft. We need improve the foundation soil. Sometimes we can place the piles under that. But if you put the slab directly on the top of this pile under large load, the slab is very easy to crack. Sometimes we will put several layers of geosynthetics together with soil, compacted soil, to make a composite foundation. On the top of that, we can put the slab on. Therefore, when the load, especially concentrated load on the slab, it will even out the pressure. So this can be used for both embankment and the composite foundation. The next topic will be seepage analysis. So we just go very quickly about some terminologies, and then we go examples. First, let's discuss about power-supported embankment design. For example, we have an embankment to be built here, and however, the foundation soil is soft, and which will cause large settlement. To overcome the settlement, there are many different ways. You can do soil improvement. You can do just a surcharge, let water dissipate and have a consolidation. After that, you put the embankment on. However, this will take time. So there's one way to do it is place piles between the barren layer and the embankment. And this practice being done in many places, including in the United States. I personally involved a project many years ago in South Carolina. So this has some useful in here. Okay. The mechanism of this design is very similar to the following pictures. On the left, you can see it's an arching bridge, and we need to pass the load from the bridge to its foundation. We have a piers here. So, but we are very easy to determine how much load will be on each pier. We can just take half of the structure here, the weight of the structure, plus the surcharge or the traffic load on the top. Then this pier will support this portion of the bridge. On the right side, it is our pile support reinforced embankment. But we can see here, it's similar to the pier, but we have piles, and in between is the soft soil. Unlike water, water cannot provide any support if we have material here. But the soil, even though it's soft, but it still can provide some support to the soil in this area. So that makes our problem a little bit complicated, because now we have both piles and the soil taking the pressure from the embankment, not like the bridge. It's very clear. So we need to determine how much will be taken by the piles and how much will taken by the soil between the piles, and how much settlement this this embankment will be after put the piles in there. So that's visual slope come into play to find out the load and the settlement, all these things. So the design item for the pile support embankment or composite foundation includes following. One is the pile top compression, which is how much load on the top of the pile, and also the compression between the piles and the pile top settlement. We need to know the settlement so we can figure out how much settlement will be on the top of the embankment or composite foundation. Also, the settlement between the piles, tension in the reinforcement, which usually is a geosynthetic reinforcement, strain in reinforcement, and the fact of safety of the reinforcement, pressure in piles, factor safety of a pile itself, and also a slope stability analysis for embankment at the edge. So these 10 items are the design items. Now let's look at an example. This example is already in the examples coming with visual slope, and you can also download from this course. This is embankment. Let me just open this file from visual slope. So open visual slope. Here's the pile supported embankment. Okay, this is the example. We have an embankment to be built. The height is 6 meters, about 18 to 19 feet tall, and the edge is 9 meters wide, and on the top of the embankment is 32 meters, and the same thing on the other side of the slope. And we have a surcharge on top. We say it's a traffic surcharge. It can either be enlarged as say it's a composite foundation. Here we have some soft layer soils here, and the bottom one is a stronger layer, which is a barren layer. So if we put these put the embankment directly on the soil, we will have a large settlement. First of all, let's just estimate how much settlement that would be. So let me just delete the piles. So the piles will be deleted, and we just see how much settlement would be put direct on the soil. We have a finite element module in the visual slope, so we can just create a mesh. After we create mesh, we need first to take the settlement from the foundation soil itself under its own weight. So we need to do two steps. So we first take this piece out. Let's say deactivate non-soil lines. So these will be gone. Oh, did I do something wrong? Okay. Deactivate, not activate. deactivate those. So this will be gone. The same thing, we can take soil out. So there's no soil, and we can run a find the element analysis. So these the settlement caused by the weight of foundation soil, which we are not interested because it happened many years ago. After that, we activate the soil. So now the embankment is on, and we run finite element again. But now we need to reset the displacement because we do not want to include the displacement caused by the weight of foundation cell. So we run it again. You can see this is the settlement caused by the embankment. We can make a contour. Here is the settlement. It's about almost like 40 centimeter, which is almost half meter. I would say at least a foot and a half of that. If you want to see the detailed number, you can draw a line under. Then this will be the settlement number. You can see the side is a little slow to the middle, is higher, some to the 3 point, almost 3 point, like a 30 some centimeter, 35 centimeter settlement. So that's the problem. So we want add the piles under that. See how much settlement will reduce. So what we will do is let's first take a look what's the material property for piles. We already discussed about the soil property. We'll also discuss our geosynthetic property in last course, but this one we take a look at the piles. I'll reset that up. Then you have when you set up these, you can have two options: one as a beam, one as a pile. For the beams, it's mainly for like showing design, and it mainly support the bending. But for the piles, it most likely it will support the vertical load. In this case, we have a piles, and the name we just called pile, and we need to provide the cross section of the pile, and also the pile cap, the area of the pile cap. The reason is if we have a very thin pile, but we have a large pile cap, in between the piles, the soil can be supported by pile cap to reduce the actual spacing. So we need to give a pile cap area, and also the elastic modulus. Pile capacity is how much vertical force one pile can support. Then the longitudinal spacing, which is the spacing going in the longitudinal direction. We say it's 1.6 in this case. And the shear capacity, how much shear force can shear the pile off. So this you need to give the pile parameters. Okay. Once we have that, we close it, and we have a pile you can use for this project. Of course, most likely you can draw the piles one by one in. However, if since we have so many, we can array it. Use the generator. From the generator, we have a pile group. Take this. So the pile group generator or array will show. So the first thing we will choose pile, and then the top of pile elevation. Top of pile elevation, then we say it is 16, and the leftmost pile x coordinate, which is 24.6, and the pile spacing. This is the horizontal spacing. We already set up the longitudinal spacing. In this case, the horizontal, we say it's 1.6, the same as the longitudinal. And then the pile length is 12 meters. And the number of piles, I calculate it's 34 piles. But if you do more, that's fine. Then you can delete it later. If you did not do enough, and you can reuse this generator to add more in. So once we have that, we click it. So the pile will be set up already. Now we can recalculate the settlement, either with visual slope or with the method. We will discuss this later. But how about let's do the finite element analysis first. We just make it. We do just activate old lines. Solid lines. So we activate all those and go to an element, and it will ask, do you want to include piles? I say yes. So the mesh now is set up. We can do the same thing as I did before. We just go to the model. We take the embankment. Just do this. Old non-soil element. Deactivate those. So that's will be gone. So the soil will be gone. Run our finite element analysis just to eliminate the initial settlement. Okay. After that, we put the noun back, and also the soil back. All right. And then we run step, but we make sure the reset display is on. So now we have the new settlement. Let's see how much that will be after we put the pile in. Before was 35 centimeters. Now we have those yellow ones. Let's see how much it should be. So now it's very small. It's only like 5 centimeters. Before was 30. Now it's about 5 or 5 something centimeters. So these are the you use from the element to estimate that. But this actually is not what we will discuss. We will go today. The one we will use today is a very easy one. So what we will do is we can just to make sure we oh sorry, I did it wrong. I just focus on one area. So we just focus on here. And what we need to do is we simply need to click this button. And it will ask you, you want a triangle pile layout or rectangle pile layout. because in the field we usually is that like install piles in the staggering way. It's not like a row by row, but it's a shift to the next row is shifted to the center of the previous row. So we want to use the triangle, but you can use the rectangle too. And also for the bottom of the pile, we ask you only consider the area of the pile, or you consider a group pile factor. Say, I would just either way. I just say just a pile. Now you have the result already. For the result, here is the pile horizontal pile numbers, horizontal coordinate, and this is the force on the pile. At the beginning, it's 25 kilonewton, and increase because here we have a slope. So the pile here will have a less load on the top of pile. And if you're going to further, then it becomes almost like a constant because the top is flat. So you have a load gradually tend to a constant. And to the right side, it will go low again. And also, it will give you the maximum pressure on the soil between the piles. So you can see here are this is the pressure here. And the pile settlement, it's about 3 centimeter, and the maximum settlement between the pile, it's so big. It's almost 1.4 meters. It's a very, very big settlement. And also give you the tension, also strain, all these numbers you can find here. For more easy, you can just click that. This will give you the tension force in the reinforcement and the strain in the reinforcement. The strain is from 1.7 to 4.6, and usually when you design that, you want to control the strain between 1% and 6%. If it's greater than 6%, then the settlement in between the piles will be too large. And plus, actually, when you use other tools, no matter how good the final element you get, you usually will not get much strain at all. So somehow, if you design that, use this will be better. But you can try using visual slope final element. Even that, it won't give you much strain. But they use this method, it will give you pretty reasonable strain. And also you can see settlement. Here you can see the top is the pie top. It have some settlement. To the middle, it's increase. Here is the settlement between piles. Here, the length of this actually is the pile cap. So the pile cap is settled, and this is actual in between the pile settlement. So you can have those numbers. So this will give you the everything you need, and you can also print a detailed report. It will in the report. It will also give you what's the arching, the height of the arching, and when we design that, the embankment thickness must be at least 3 times of the arching height. Otherwise, it will experience settlement on the top of the embankment. It will be like you will see some dimples on the top. So you must have at least 3 times of the arching height. I had a project. I was helping someone it had that type of problem. So this is what you need to be careful. All right, so that's what we do with the pile supported embankment. The last one you want to check, see if the embankment will fail for the slope. So we just do a quick one. Just a simple one. We have a quick stability analysis. So just say we have 500 try. It's a circular failing. Okay. We have a very large. Actually, we need to move this a little bit to here. It shouldn't be a problem because the initial settlement is so the factor of safety is so high. It need to continue to go further. Maybe I wonder if we'll go slides from here, but you need to run a slope stability analysis. Make sure it does not fail. But currently we have a very high one. So this is the total design for the pile supported embankment. As I mentioned, you can also use this program for a composite foundation design. Okay. The first topic is here, and we go to the next one. Next one is the seepage analysis. So for the seepage analysis, I just want to go ahead, give some terminology. We're clear about the terminology. Water head, sometimes called pressure or pressure head, or elevation. What's the relation of those? Most of us probably know that, but I just make it clear anyway. For example, we have a point here. The elevation of this point is 5.5 meters. And above that, we have a water table. The water table is at 10 meters. So the pressure, or the pressure head of this is the distance from here, the difference of this. It's like 10 feet minus 5.5 meter, so which is 4.5. It's too small for you to see. So the actual water pressure at this point is 4.5 meters. But the head of this point is the pressure plus the elevation. So pressure is 4.5, elevation is 5.5. So you add these two numbers together, the head of this point is 10 meters. So that's the relation. The same thing for this one. It's a higher, it has a less pressure, but it has high elevation. So this point will end up with the same head. It's also 10 feet. So all the points below this water table from here to here are all 10. The water head will be 10. So I just want to give a little bit clearance for those terminology. And the next one, we call it confined seepage. Confined seepage means if we have a model, a dam model here, and each boundary supposed to be all defined. Once it's all defined, we call it confined seepage. For example, this boundary, and this boundary, in those boundaries, the water cannot flow through. So we know there's no water flow perpendicular to this boundary. It cannot go this way, cannot come in. The same thing, cannot go through this way, cannot come up. This is the one type of a boundary. It's a flow boundary. And the second type of boundary is a water head boundary. For example, from here to here, we said the head is known. The head is the same elevation as this water table. But from here to here, since we have a water table under, so we know what's the water head under this water. But here above, it's unsaturated soil. So we will know it's unsaturated soil. And the same thing here, it's all covered by the water table here. So for this example, it's totally confined. It's the boundary conditions are clear. The next one, that's the one we had the other one. Also use this for the first class for the slope stability analysis. This is then we have a water reservoir behind, and we know what's the height of the water table on the reservoir. However, we do not know inside of them what type of a water table it would be. So here it communicates with the air above, include here. So the program need to find out what is the saturated and unsaturated line, the boundary between the saturated and unsaturated line. So in this case, we call it unconfined seepage. So this is a little bit difficult than the other one. Okay. So when we do our project, we needed to know our boundary condition is confined or unconfined. Many seepage program out there, they are very easy to use. The problem for our geotechnical engineers, sometimes we are not so sure about the boundary for the seepage analysis. We are very clear about the force seepage, the displacement boundary condition, but not very good on the seepage boundary. So I just give you some idea. Okay, now let's open up the examples. So I'll just first open that, and this is the one I just described. Here is a geosynthetic line. I take that out for a moment. So say this is the then we know the water table all along, and we need to run a seepage analysis. It's a confined condition, so we just run a confined seepage analysis. Okay, so we have that seepage. We can draw an equal potential line. So those are the equal potential line. From here to here, the head are all the same. From here to here, the head are all the same. Same thing for this. Each line is something like that. This is the equal potential line. And we can also draw a flow line. Flow line. And you can see the flow is from this side going to this side. These are the flow lines. When we in the soil mechanic class, we know the flow line should be perpendicular to the equal potential line. If you measure it, you will find that it is perpendicular. However, that's only for the permeability for the soil in both directions are the same, then it will be perpendicular. But if it's not, then it will not be perpendicular. You can try with visual set a different different permeability number, or some place called the conductivity number into it. You will find it different. So once we have that, we have the flow line, we have equal potential line, and also sometimes we are very considerate about the discharge, how much discharge it will be. So you draw a line here, it will tell you the discharge from here to here, it will be 1.23 cubic foot per second per foot. So this is the discharge. Also, it will give you a Y exit gradient. This gradient, if this gradient is greater than 1, which means the water can even break the soil. But if it's less than 1, it will not. Sometimes if you go application for Army Corps of Engineers, they will ask you if you want to build some buildings here. They will let you check what the Y exit gradient it will be. So this is the way you can provide those. All right. So this is seepage. If we want to simulate, say, a drain, you can use geosynthetic line to put it into it, and then you can simulate it. That's just activate this one. So, for example, now we put a drain at the toe of the slope, and then we rerun confined seepage analysis. So we will see. Now this is a little bit different from the others. Along this line, it only equals the head is equal to its vertical coordinates, which means the pressure is 0. So since if there's a pressure, the water will go away. So that's what you simulate for the drain. You can also draw flow lines. See, the water will go to here because it's easy to drain out. So that's the seepage analysis you can use for this type of analysis. Now, next one, we go a little bit further. For the next one, the one we just discussed about. In the first class, I mentioned if you do seepage, just run the slope stability does not include the seepage force. You can get that, but you can also include seepage force. I'm not going to repeat that today. So let's just do one. So this one we do not know inside of them what's the boundary between saturated and unsaturated soil. So we need to do analysis. We do unconfined. This is a theoretical line analysis. We click on this. So we do a static state seepage analysis. It seems to be pretty fast. So you will see it looks like that. If you use the contour lines, you probably will see here. So this is very clear. Below that is a saturated. If we right-click the mouse button, we will see pressure is about 0.9. But if you go in here, still have some pressure, and then you go further, the pressure will be 0. So it's the saturated unsaturated line is like here. So this is the true boundary line. So with this, you will know where the soil is saturated, where the soil is unsaturated. This is the way you do. But in this case, those lines are not equal potential lines. These lines is a pressure head line. So we want to be sure. You should not draw a flow line with this because they are not the same thing. So if, for example, if we want to do a equal potential line, we can still do it. Okay, finished. So this is the equal potential line. It's similar to what we have. Above that is unsaturated. Below that is saturated. If you run a flow line, the flow line is going from here to here. So that's what you can have. And also, we want to simulate, say, if we have a sheet pile, try to make it more impermeable. So what we can do is we draw a limiter line here, a limiter line, draw a limiter line here. And then we run a seepage analysis again. It's still unconfined. So it's finished. And if you draw that again, you will see it's going down a lot because the water cannot go through that. That's what you simulate for the sheet pile to or slide cut off the wall. You can simulate with a limit line. All right. Finally, we so far what we did was all for static seepage analysis. But many cases, some cases, you need to know the transit state, which means you want to consider, say, we just build this dam, we now put the water in, we want to see how fast the water will go into the dam, and eventually eventually it's going to be a static condition. But say if we want to run after 5 hours, what's going to happen? So let's just take a look. Here we choose, say the elapsed time is 5 hours. The transit seepage analysis. So it's done, and you will see it's only going to here a little bit. It's 5 hours. How fast or how slow, it really depends on the permeability you put into the soil. So we will, after we finish, we will go back to see where we put the permeability for the soil. So this is a 5. I just do a very quick one, say, let's do 200 hours. 200 hours. So it's coming in more, and you can even do more, say 500 hours. It should be coming further. Yeah, it's more and more towards the static condition, something like that. So it's really depends on what kind of permeability you put in. So Visual Server does allow you to do the transit. However, I have to admit, I believe actually most the computer seepage analysis program, they all can do static analysis. Many can do transit too. However, if you have multiple different materials, it will make transit calculation very difficult because the transit, you need a time increment. The time increment actually is controlled by the permeability. If you choose the too large or too small, it will cause the calculation not stable. If you have one material, it's easy to figure out. But if you have many different materials, it's difficult for the program to use which one to determine the time increment. So for visual slope, if you have a different material, the result give to you for the transit, it's just an estimate. I just need to let you know for that. Okay. Finally, we just look at the soil property just to see how can you put the material into permeability into it. And the one you already set, you choose this, you edit. And the first page, we all have those in the slope stability analysis. And for the next page, you can have a Seepage parameters. This is for horizontal permeability and the vertical permeability. You can put that into it. All right. So now it's today's topics are all covered. I wonder anyone would have any questions to ask. You can turn on your microphone to ask questions. If not, you can always send questions through email. If you have a problem with modeling, just send an input file with the questions. We will resolve that for you very quickly. And also, you can go to Visual Slope Help menu. There are many videos you can watch. And also, the next one will be next class will be showing design. I hope you can come and it will be helpful. Thank you so much. Have a good weekend. Bye.